Good day, everyone. I am Mam-Gen from Group 1, and our topic is Perpetual Calendar. For your learning task, you're going to solve for any day of the dates, as well as you're going to apply concepts of number theory in Perpetual Calendar. But before that, let us have first our short activity. Our activity entitled Tell the Right Date. For the instruction, choose the right date of each Philippine holidays last year 2020. Type your answer in the chat section. For number 1, we have New Year. Type your answers now. And the correct answer is letter A, Wednesday, January 1, 2020. For number 2, we have National Heroes Day. Type your answers now. And the correct answer is letter C, Monday, August 31, 2020. For number 3, we have Bonifacio Day. Type your answers now. And the answer is letter D, Monday, November 30, 2020. For number 4, we have Bataan Day. Type your answers now. And the correct answer is letter B, Thursday, April 9, 2020. And for the last question, we have Rizal Day. Type your answers now. And for the correct answer is it's letter E, Wednesday, December 30, 2020. So here's the right date for the 5 questions for our 5 Philippine holidays. Now, our question is, are the dates given will fall at the same days this year, 2021? How about last 2019? Before we answer this question, let us have first a short history of calendar.
Let's now have an overview of the calendar. First is its etymology. Calendar came from the Latin word calendarium, meaning interest register or an account book. And meanwhile, calendarium came from the Latin word calende, or the day of the announcement of the important dates of the year. This calendar takes place on the very first day of the year. Okay? So let's define what is a calendar. Calendar is any system for dividing time over extended periods, such as days, months, or years, and arranging such divisions in a definite order. Pictured below is a Chinese calendar dated from the 18th century. So let's now have an overview of the history of the calendar. At the early times, we have two types of calendar known as the lunar and solar calendars. We had this in Egypt and Mesopotamia. Then, it was considered that the lunar calendar was the more primitive one, while the solar calendar was the more accurate one. And actually, our calendar for our current calendar is also based on a solar calendar. Then, the Roman calendar came on the 1st century BC under the rule of Julius Caesar. It was called the Julian calendar. Eventually, this Julian calendar will be found to be erroneous at some points and leaving the cycle 10 days lagging. So, to remedy this lag of days, we had the Gregorian calendar established under the reign of Pope Gregory XIII. It was through the efforts of Christopher Clavius, a Jesuit priest, where the Gregorian calendar was established. So eventually, this Gregorian calendar began to spread on different papal states. Yes, different papal states. However, it was only until 1940s, later 1940s, that the last nation to adopt this Gregorian calendar was China. So, what's a perpetual calendar? A perpetual calendar is a device that makes it possible to find the correct day of the week for any date over a wide range of years. So it's not actually a perpetual calendar per se, but it is a calendar for a very wide range of years. So in this picture, it was said that this calendar can give an accurate day and date for 50 years, and it was dated 2003 until 2052.
So before we go into the actual computation, let's first discuss some of the assumptions in trying to find the day of the week using the perpetual calendar. So first is the definition of a leap year. So according to Christopher Clavius, leap years are years divisible by 4, but not including the century years, even though they are technically divisible by 4. And among the century years, only those that are divisible by 400 are considered leap years. So for example, the year 1700s is not a leap year. The year 1600s is a leap year, and the year 2000 is a leap year. Second assumption, that is March, the first month of the year, and then January and February are the 11th and the 12th respectively. So this table represents the values of M for every month, which will be very helpful in our discussion later on. And the third assumption is that Sunday is the first day of the week with W equal to 0, and where W is a notation for the day of the week. That would mean 1 is Monday, 2 for Tuesday, and so on and so forth. So this table represents the values of W for each day of the week. So the concept behind trying to find the day of the week using the perpetual calendar is the idea that 365 is congruent to 1 modulo 7 and 366 is congruent to 2 modulo 7. That means for every year, whatever the day is today, after 1 year, that day would be given an additional 1. So for example, if the day is a Monday, the next year of the same date would be a Tuesday. However, if it's a leap year, then instead of a Tuesday, it will become a Wednesday. If the day is a Monday, the next year of the same date would be a Wednesday instead. So the general formula for getting the day of the week is this. So we tried to find a formula for that idea that 366 is congruent to 1 modulo 7 and 366 is congruent to 2 rather, modulo 7, and 365 is congruent to 1 modulo 7. So this is our formula. D of y sub 1 represents the day of the base year. So this is the day of March 1 of any year. And this one is the elapsed year between the 2 years we're trying to get. And L is the number of leap years between our y sub 1 and y sub 2. So for smaller numbers, it is quite easy to calculate L since L is the only missing variable in our formula. So for example, if the elapsed year is 50, we just simply get the greatest integer of 50 over 4, so that's 12. So in an elapsed year of 50 years, there are 12 leap years. For bigger numbers, however, we have to recall Christopher Clavius' definition of a leap year. So it is those years divisible by 4, but not including the century years. So we subtract the century years. And then we add again those century years that are divisible by 400. So if we try to reduce this equation here, we get this reduced form. L is equal to the greatest integer of y over 4 minus the greatest integer of y over 100 plus the greatest integer of y over 400 minus 388. So now we have our equation for L. There is also another form of L if we try to represent our y as 100c plus y. So for example, the year 1772, we rewrite that as 17 times 100 plus 72. So our small c is 17 and our small y becomes 72. So here we just simply substituted from the original equation of L, this one. And if we reduce this, it becomes 24c plus the greatest integer of y over 4 minus the greatest integer of c over 4 minus 388. So now we have two equations of L. Let's try to put that in our original formula. So this is our original formula. And if we just change L to the two equations we solved a while ago, so we will have these two equations. So basically, you can already use this. But this still looks a bit complicated. So let's try to simplify that. So in the book that we based this discussion on, they decided on a fixed date, that's March 1, 1600, that fell on a Wednesday. So in our formula, we just simply have to substitute our year sub 1, or y sub 1 rather, of 1600s, and then our d of y sub 1 would be 3 for Wednesday. So we substituted that in one of our equations that we got. So if we reduce this by getting the modulo 7 of each of the terms, when reduced, this becomes this equation. So this is our final equation. But remember, this formula is only used for getting March 1 of whatever year, using the base year March 1, 1600. For example, question 1. On what day did March 1, 1756 fall on? So we just simply copied our formula here. And then the given, so the only thing that we can actually use from the given is the 1756. So we re-express our 1756 here as 17 times 100 plus 56. So our small c is 17 and our small y is 56. So the solution, we just simply substitute our c and our y, our c and a y from our given to the formula. So that's 3 minus 2 times 17 plus 56 plus the greatest integer of 17 over 4 plus the greatest integer of 56 over 4 modulo 7. So when we add all those, we get 43 modulo 7, which is congruent to 1 modulo 7. Now this means that March 1, 1756 fell on Monday. So just an additional question. If March 1, 1756 fell on a Monday, what day of the week was March 1, 1766? Now, there are two ways in which we can approach this problem. One is by ignoring March 1, 1756 fell on a Monday, so we just ignore that and simply solve for March 1, 1766 using the formula, using the same process that we did on that last item. But in that process, we used March 1, 1600s as our base year. The second approach is if we use March 1, 1756 as our base year instead. So if we use the year 1756, we use the original formula, the one where we did not substitute yet the L and we did not substitute yet our d of y sub 1. So this is our original equation. And it is quite easy to solve for the elapsed year. So that's 1766 minus 1756 is just 10. Now for the L is basically how many leap years are there between those two dates, between these two dates. So since the elapsed year is 10, how many leap years are there? Simply the greatest integer of 10 over 4, which is equal to 2. So let's try to substitute now the given 176. In order to get March 1 of 1766, we add 1 for since March 1, 1756 fell on a Monday, so that's 1 for Monday, plus 10 for the elapsed year, and then plus 2 for the number of leap years between those 2 years. So we get 1 plus 10 plus 2 is congruent to 6 modulo 7. Therefore, March 1, 1766 fell on a Saturday.
So previously it was discussed on how to obtain the day of the week of a given year, or the day of the week of the same date but different years. In this section, we're going to discuss on how to obtain the first day of the month of a given year. So we will know, for instance, how to obtain the days of the week of January 1 and April 1 of the same year. And same with Miss Sheinna discussed earlier, here are the critical items. First, the first month of the year is assumed to be March. Second, the first day of the week is assumed to be Sunday. And since we are calculating the dates within the same year, we have to know the number of days in between those dates. The first strategy that we can apply is to use the table of increments. So this table of increments is the first of the two strategies that we can actually employ. So we have here a table with 5 columns. On the first column are the first days of all the months in the year, starting March, of course. And then the second column represents the number of days in between two consecutive months. So for instance, for the row January 1, 31 is the number of days between January 1 and December 1. And we have the modulo 7 on the third column. On the fourth column, we have the interval between the first day and March 1. And of course, the modulo 7 at the last column. And we can use this table, for instance, if we're trying to find a certain day of week of a certain first day. So, for example, today is January 2, 2021. And we know that yesterday, which is a Friday, it's January 1. So, Happy New Year. If we want to know the day of the week for Feb 1, we have to just look at Feb 1 row and get the third column, which is 3, and add that 3 to the corresponding day number on January 1. So we know and stated earlier that January 1 is a Friday, so that's 5 modulo 7. So 5 mod 7 plus 3, so that's 8 mod 7 or 1 mod 7, giving us Monday. So Feb 1, 2021 should be a Monday. So that's the first strategy. The second strategy is a formula discovered by Christian Zeller accidentally, or by trial and error rather. And I'm just glad that we have this formula because we don't have to memorize all the increments in the table. for us to calculate the first day of the month. So we have here W, which is the day number of the date of interest, or the day number of the first day that we want to calculate. And W equals D sub n plus the rounded down value of 2.6m minus zero point 0.2 less 2 modulo 7, where D sub n is the day number of the reference date and m is the month number of the date of interest. So again, we have two strategies, the table of increments and the formula. So let's apply this. So for example, Nathan brings his score only when his payday falls on a Friday. His salary is credited every 15th of the month. Given that March 1, 2020 and 2021 are Sunday and Monday respectively, for the year ending December 31, 2021, how many times will Nathan bring his score? So in this problem, we actually just have to count the number of times that Friday, which is Nathan's payday, will fall on the 15th of the month. So we know that um, the difference between the 15th day and the first day is 14, which is basically congruent to 0 modulo 7. So whatever the day of the week for January 15 or the 15th of the month, that's also the same as the first day of the week. So we just have to use the formula stated earlier. So since we were given that March 1, 2020 is a Sunday and March 1, 2021 is a Monday, then we have D sub n for January 15 and Feb 15 as 0 since they are Sunday. And for March 1, 2020 and onwards, our D sub n should be 1 since it was stated that it was a Monday. So we just have to apply the formula and input the correct numbers. So starting with January 15, we have the D sub n of 0 and January, given that March is the first day or the first month rather of the year, we know that January is the 11th. So we should supply 11 for M. So W equals 0 plus the rounded value of 2.6 times 11 minus zero point 0.2 less 2 modulo 7. So that gives us 0 plus 28 minus 2 mod 7 or 5 mod 7 or Friday. January 15 is a Friday. On the next month, which is Feb 15, we just have to replace M with 12 since Feb is the last day of the year or last month of the year rather. So calculating for the day, we will obtain 1 mod 7 or Monday. And then for March 15, it was given already and it is Monday. And for April 15, since it's a new year relative to Feb 15 and January 15, instead of using d sub n equals 0, we have to use 1 as the d sub n. So applying the formula and using 2 as the m, because April is the second month of the year, we will obtain 4 mod 7 or Thursday. And then we just need to apply the formula for the rest of the months. And then after applying the formula, we can summarize the days that we calculated. And so summarizing what we obtained, we will figure out that there are actually 2 Fridays falling on January 15 and October 15. So to answer the question in this example, Nathan just needs to bring his car only twice in 2021.
Let us have the fourth example. The fourth example, entitled The Day of Valor, or the Bataan Death March. Bataan Death March started in Maribeles at the southern tip of the Bataan Peninsula on April 9, 1942. The prisoners were forced marched from north of Bataan to San Fernando and then taken by rail in cramped and unsanitary boxcars farther north to Capas. So here is the map that shows the distance traveled by the prisoners from Maribeles Corregidor going to San Fernando, Pampanga. After they reach San Fernando, Pampanga, they use train to reach Capas Tarlac, and that is their final destination. In our history, the government of Bataan the government of Bataan tribute a large cross for those Filipinos who died during the death march. This large cross contains 36 floors, and the intersection or the cross section here is the 30th floor, and the remaining 6 floors are not allowed by the other personnel. So the question is, what day is April 9, 1942? And how about April 9, 2030? So let us find out what day is April 9, 1942. What I have here is a corresponding number for each month. So we're going to number March as 1, April 2, May is the 3rd month, June is the 4th month, until February is the 12th month. Our given is April 9, 1942. So for our solution, we're going to use the formula W is congruent to D plus the greatest integer function of 2.6 times M minus 2 tenths minus 2 times C plus Y plus the greatest integer function of C over 4 plus greatest integer function of Y over 4 modulo 7. So we're going to identify the variables M, C, and Y. Since our month is April, so we're going to choose 2, which is M is equals to 2, since April is the 2nd month. For century, we have 19, since the year is 1942, and the year is 42. Upon substituting the given, we have W is congruent to 9 plus the greatest integer function of 2.6 times 2 minus 0.2 or 2 tenths minus 2 times 19 plus 42. So C is 19, M is 2, Y is 42 plus 19 over 4 or the greatest integer function of 19 over 4 plus the greatest integer function of 42 over 4 modulo 7. By simplifying, we have now W is congruent to 9 plus 5.2 minus 0.2 or 2 tenths rather, minus 38 plus 42 plus 4 plus 10. So we have now 9, W is congruent to 9 plus 5 minus 38 plus 42 plus 4 plus 10 modulo 7. So W is congruent to 32. It is congruent to 4 modulo 7. And we all know that 4 is Thursday. Therefore, April 9, 1942 is Thursday. How about April 9, 2030? So for our solution, we're going to use the same formula. We're going to use the formula W is congruent to D plus the greatest integer function of 2.6 times M minus 2 tenths minus 2C plus Y plus the greatest integer function of C over 4 plus the greatest integer function of y over 4 modulo 7. So our month is still April. So our M is 2, our C or century is 20, and our year is 30. We're going to substitute this in our formula. So we got W is congruent to 9 plus the greatest integer function of 2.6 times 2 minus 2 tenths minus 2 times 20 plus 30 plus the greatest integer function of 20 over 4 plus the greatest integer function of 30 over 4 modulo 7. So we have now W is congruent to 9 plus 5.2 minus 2 tenths minus 40 plus 30 plus 5 plus 7 modulo 7. So we have now W is congruent to 9 plus 5 minus 40 plus 30 plus 5 plus 7 modulo 7. So we have now W is congruent to 16, which is also congruent to 2 modulo 7. And 2 corresponds to Tuesday. Therefore, April 9, 2030 is Tuesday. Let us have the last example.
Let's now move on to this fifth example, the Christmas long weekend. The Christmas day of 2020 commenced a long weekend since it fell on a Friday. However, because of the prevailing pandemic during the year, you and your friends were not able to make the fullest out of this holiday. So, you became interested when will be the next long weekend in the next 10 years, where its beginning is Christmas Day. Determine the year when will this happen. So, on this problem you are asked, when will be the next Christmas Day that will fall on a Friday for the next 10 years? So that's the rephrase of the problem. So our solution will be guided by this theorem discussed earlier. So W is linearly congruent to D plus the floor of 2.6 times M minus 0.2 minus 2C plus Y plus the floor of C over 4 plus floor of Y over 4 mod 7. We work on the assumption on the mentioned assumptions. Okay, so let's start our solution. So we want December 25 to fall on a Friday on the next 10 years. So we're interested on the years 2021 until 2031. We want to find the year or the years on that given span where December 25 will be a Friday. So, as guided by the theorem, we will have this following linear congruence. 5. We set 5 for because Friday is coded as 5, then the day 25 plus the floor of 2.6. What's our M? It's 10 because we work on the assumption that March is the first month. So 10 will be December will be the 10th month. So 10 minus 0.2 minus 2C. Our C will be 20, right? Because we're interested on the years 2021 until 2031. Okay. 2 times 20 plus Y, we don't know the Y. So plus 20 over 4 plus the floor of Y over 4 mod 7. So we work on this linear congruence to solve for the year where December 25 will fall on a Friday. So let's work this out. So 25 plus the floor of this. So what will be the answer for this expression? It's 25.8 minus 2 times 20 is 40 plus Y plus the floor of 20 over 4 is 5 plus floor of y over 4 mod 7. Okay? So, what's the floor of 25.8? It's 25. So 25 plus 25 minus 40 plus y plus 5 plus the floor of y over 4 mod 7. Okay? Are we clear? Yes. So we just make the right hand side more tidy. So we will have 5 is linearly congruent to 25 plus 25 minus 40 plus 5 is just 15 plus y plus the floor of y over 4 mod 7. Okay? Which entail negative 10 is linearly congruent to y plus the floor of y over 4 mod 7. Okay? Which is just equivalent to 4 is linearly congruent to y plus y over 4 mod 7. Okay? So, we work now on this linear congruence. Okay? So, we want December 25 to fall on a Friday, and we are considering 10 years from 2021 until 2031. So we consider the values of y 21 up to 31. Okay? So when we evaluate this linear congruence with values of y equals 21, 22, 23, 24, 25, 27, 28, 29, 30. Yes, up to 30. 31. We will find that 4 will not be linearly congruent to y plus floor of y over 4 mod 7. Again, when given these values of y, 21 up to 31 except 26, this linear congruence will not hold. So, upon evaluation, checking, you will find out that it's only on y equals 26 where this linear congruence will hold. So let's try. So let's plug in 26 on the right hand side. So 26 plus 26, the floor of 26 over 4 is just equal to 26 plus 6, which is equal to 32. Okay? And 32 happened to be linearly congruent to 4 mod 7. So, our linear congruence hold. And thus, we can now conclude that, therefore, the next time that December 25 will fall on a Friday is on 2026.
For our performance task, the goal is your task is to inform netizens about a certain scenario including its past, present, and the future. You will choose among important events such as important events in your life, someone close to you, to your client, to a famous personality, or in your country. Then you are going to collect important records such as news, pictures, articles, videos, and the like. In your compilation, apply the concepts of number theoretic functions in the calendar, then submit your solutions to the head of organization or manager of the company. We have here 4 roles such as blogger, travel entrepreneur, historian, or writer. And the audience are netizens, head of organization, or manager of the company. The situation is you are hired in a company or join in an organization and ask you to upload your outputs in a certain channel, Facebook group, or website to inform netizens. The products are blog, travel clips, multimedia presentation, journal, article, or essay. The output is graded according to scoring rubric. So here's the scoring rubric of performance task. So we have here the number 4321 and the criteria are authenticity of data, coherence, accuracy of computations. Then we have another two later. So for authenticity of data, you get 4 if your data is authentic and updated. 3 if it is reliable from the sources. 2 if the data used are not authentic. And 1 if the data you get is not useful and reliable. For coherence, the output is correct, systematic, and consistent, which is 4. The output is correct and logical, which is 3. The output has minor errors, and the output has major errors for 1. For accuracy of computations, you got 4 if the computations are clear, accurate, and supported with correct and detailed interpretation. Number 3, computations are accurate and supported with correct and detailed interpretation. You got 2 if computations are correct but interpretation is incorrect. You got 1 if most of the computations and interpretations are erroneous. The remaining 2 criteria are realistic, the content is informative, highly favorable to the audience, and realistic, which is 4. You got 3 if your content is informative, favorable to the audience, and realistic. You got 2 if the content is less informative, less favorable, and less realistic. You got 1 rather, if the content is not informative, unfavorable, and unrealistic. For the last criteria, we have application of concepts of number theory and calendar. You got 4 if your output use the concept or the usage of concept is correct and justified. You got 3 if the usage of concept is correct. You got 2 if the usage of concept is correct but not justified. And you got 1 if the usage of concept is incorrect. So the total of 20. The highest score is 20 and the lowest score is 5. So this will be the end of our presentation. Thank you for listening.